Hey, how's everyone doing?
I'm good. How about you?
Sorry?
How are you doing?
Doing good? Doing good?
Did you get your McDonald's?
I did not today, unfortunately. Haven't been getting it every day, but not today, no. Why, they got anything new and exciting?
Spicy nuggets, I think.
Spicy nuggets? I thought those have been around for a few months. Something like that.
Oh,
I didn't have them once, so I'm a big fan of those, but not as good as Wendy's spicy nuggets, I think.
Yeah, you're right. You're right. You're a king for that. I'm not a McDonald's expert.
Yeah. All righty. Oh, whoops, no, hang on. Wrong one. Wrong one. Five Guys fries better than McDonald's fries? Well, I mean, like, you're also paying a whole lot more at Five Guys, but I mean, very true. All right. Okay. So we're going to finish up talking about gradient and the directional derivative. So that was 14.5. Lovely. Okay. Okay, so we saw last time the gradient of f for a function of, let me just write it like this. So the gradient of f is just a function which assigns a vector to every point. So if you're a function of two variables to every point in the plane, it assigns a vector, the partial of f with respect to x at the point, and the partial of f with respect to y at the point. And if you're a function of three variables, it's a three-dimensional vector, f sub x, f sub y, f sub z. So I didn't plug in a point in here. It's just sort of shorthand, but like if we were at the point, for the first one, if we were at the point AB, it'd be partial of f with respect to x at the point AB, partial of f with respect to y at the point AB, so on and so forth. So that's the gradient of f. And then we saw if u is a unit vector, so we need u to be a unit vector to calculate the directional derivative. So if u is a unit vector, and p is a point, I'm going to use p because it can stand for either a point in R2 or a point in R3. And it works the same way. So P is some point. So then the directional derivative of a function f that's supposed to be an at the point P in the direction of the unit vector u so it's capital D sub u for the direction of f at the point P. So that's going to be the gradient of f at the point P. So evaluate the gradient at that point. And then you dot it with the unit vector u. And I want to emphasize again, you're not always going to be given a unit vector, but when calculating a directional derivative, you need to get a unit vector in the direction we're taking the derivative. So it's a gradient at the point dot the unit vector in the direction we want to take the derivative. Okay, so let's look at this formula here and see if we can figure out any properties of the gradient in the directional derivative here. Let me just rewrite the whole thing. So we have the gradient of f at our point, which is a vector, dot the unit vector in the direction that we're taking the derivative. So we have a dot product of two vectors here. Well, we know you should have this drilled into your brain. The dot product of two vectors. So if this is, say, our direction, here's our point AB, or our point P, and say this is whatever, that's a point P. That's a gradient of f of P. So if theta is the angle between 0 and pi between the two, between the vector u and the vector, the gradient of f, then this is, the dot product is the magnitude of the gradient of f at our point times the magnitude of u times cosine of the angle between the two vectors. But what is the magnitude of u? It's 1, right? It's a unit vector. We made sure it was a unit vector. Okay, that's supposed to be 1. So the directional derivative is going to be equal to the magnitude of the gradient at the point times cosine of theta, where theta is the angle between the unit vector u, the direction we're taking the derivative in, and the gradient vector itself. Okay, so what does this tell us about the directional derivative? Well, we know cosine of theta lies between -1 and 1. So it's -1 if the gradient of f, or if the angle between the two vectors is pi. So if u is pointing in the opposite direction of the gradient of f, cosine of theta is -1. And if u, the direction we're taking the directional derivative, points in the same direction as the gradient of f, then cosine theta is 1. Whoops. So we know that the directional derivative, so if we're considering all directions u, we can take the derivative in. We know the least the directional derivative at a point can be in is negative magnitude of the gradient. So that's when cosine theta is -1. In other words, when theta is equal to pi. In other words, when we're taking the derivative in the direction of negative of the gradient, right? So when the angle between u and the gradient is pi, they point in opposite directions. So when we're taking the derivative in the direction of negative of the gradient, the directional derivative is going to be negative magnitude of the gradient at the point. That's the least it can be. And the most it can be is magnitude of the gradient. And that's when cosine theta is equal to 1. In other words, when theta equals 0. In other words, when we take the directional derivative in the direction of the gradient. So let's summarize that in the following theorem. So if our gradient is not the 0 vector, which can happen, strange stuff happens when the gradient is 0, but we're going to assume the gradient is not the 0 vector. Then we know that the gradient itself is a vector, and that vector points in the direction of maximum increase. Oops. So points in the direction of maximum increase of our function f. So in other words, if you're at the point P and you want to know what direction do you want to go where your function is going to increase the fastest? Well, you look at the gradient's going to point in the direction you want to go. Where if you go in that direction, your function is going to increase the fastest. And the rate of that increase, in other words, the directional derivative in the direction of the gradient is the magnitude of the gradient at the point P. So the gradient tells us two things. It tells us the direction to go to maximize the increase of your function. And it also tells us the rate of that increase In other words, a directional derivative when you go in that direction. And it's just the magnitude of the gradient. So similarly, if you want to look at the direction of greatest decrease, it's negative of the gradient, right? The gradient points in the direction of greatest increase. It makes sense that if you want your function to decrease the fastest, you go in the opposite direction. And that's exactly what you do. So negative gradient of f, remember that's a vector, so negative points as a vector pointing in the opposite direction. Points in the direction of greatest decrease. Of f. And the rate of change in that direction is negative gradient of f at b. So number 3, so the third thing, which was not immediately obvious from what we said, but it's a fact. So the gradient is also normal to the level curve or level surface, depending on whether it's a 2-dimensional or 3-dimensional function, or a function of 2 variables or 3 variables, to the level curve or surface at the point P. Oops. And I'll draw a picture to show what I mean there. Okay, so the big take home is this first guy here, and the second guy is kind of like the opposite of that. But basically the gradient, so if we look at the directional derivative, we're at a point, and we look at all possible directions we can go in, and we want to know which direction to go in to maximize our rate of increase of our function. Which direction we want to go in so our function is going to be increasing the fastest? Well, the gradient at the point points in the direction of greatest increase. And moreover, the rate of increase, in other words, the directional derivative in the direction of the gradient, is the magnitude of the gradient. That is important. And similarly, negative of the gradient points in the direction of greatest decrease of your function, and the directional derivative in that direction is negative the magnitude of the gradient. Any questions about that? Okay, so for that third bit, here's what that looks like. So let me do some. Suppose here's a contour map. Oops, didn't want to do that. Suppose here's a contour map of a function. Suppose this is like these are level curves of our function of 2 variables. So everything on this first curve on the left is f of xy equals 1. So these are all the points that you can plug in to your function where you get the value 1. The other one's f of x, y equals 2. The third is f of x, y equals 3. I'm just using 1, 2, and 3 as an example. So if you pick a point on one of these level curves, so let's pick a point, say like right here. The third thing here tells us that the gradient of f at that point is going to be a vector which is normal to the curve. In other words, it's if you look at the tangent line to the curve, it's going to be orthogonal to the tangent line. So suppose this is the tangent line to the curve at the point P. Call it lovely. Call that guy P. It's going to be orthogonal to the tangent line. Moreover, sorry, this vector is the gradient of f of P. Moreover, it's going to be pointing in the direction of increase in the function. So it's going to be pointing towards the next level curve up, right? So the gradient of f points in direction of increase of the function. And sort of intuitively, this makes sense because, so suppose you're on a level curve, right? If you stay on a level curve, your function stays, the value of the function stays the same. Suppose you want to go in the direction which increases the value of your function the fastest. Well, how would you travel? Well, you would obviously go towards the next level curve up, right, in the direction of increase of your function. But you also want to get away from the level curve you're on as fast as possible, right? Because if you're on the level curve, then your function is the same. So you want to get away from there as fast as possible. Well, the way to do that is to move in a normal direction to your curve, right? Orthogonal to the tangent line. And that's exactly what the gradient does. So, and that's true for any point you pick. Whoops. So if I pick a point on here, the gradient of f at that point is going to be orthogonal to the curve. If I pick a point right here, the gradient is going to be orthogonal to the curve, etc. And we'll use that a bit when we talk about Lagrange multipliers to kind of explain where it's coming from. But really, the more important one is for level surfaces. So if I have a level surface of my function, so suppose this is the level surface f of x, y, z equals k. So it's a level surface for a function in 3 variables. And I pick some point P. So if I look at the tangent plane, pretend that's a tangent plane, to the surface at the point P, the gradient of f is going to be normal to the tangent plane. And we'll do an example of that in just a second. But yeah, let me do one example for maximum rate of increase real quick. So suppose suppose our function is x to the 4, y to the negative 2. And our point P is the point 2, 1. So let's find the unit vector which points in the direction of, let's say, maximum increase of f at P and let's find that maximum rate of increase. In other words, let's find the directional derivative in the direction, the maximum of the directional derivatives over all the possible directions. Okay. So from our theorem before, it says the gradient is going to be pointing in the direction of maximum increase. So we want to find the unit vector pointing in the direction of max increase. Well, that's just going to be the unit vector pointing in the direction of the gradient. So let's find the gradient of f at our point and turn it into a unit vector. So not plugging in a point yet. So the gradient of f is, so the partial of f with respect to x is going to be 4x cubed y to the negative 2. And then the partial of f with respect to y is going to be negative 2 x to the 4y to the negative 3. So we want the gradient at the point. So evaluating that. So at 2, 1, x is equal to 2, y is equal to 1. So we get 4 times 2 cubed, which is 32, times 1 to the negative 2. So we get 32. And then negative 2 times 2 to the 4, so negative 2 times 16 times 1 to the negative 3 is negative 32. That's a gradient at our point. So the unit vector we want to, pointing in the direction of max increase is just going to be, you turn the gradient at the point into a unit vector because the gradient points in direction of max increase. Whoops, sorry. No, it's just going to be the gradient divided by the magnitude of the gradient. What is the magnitude of our gradient? Yeah, so you could say square root 2048. That's one way to do it. Or you can make your life a little easier. And so here's a nice trick. Here's a nice trick you can do to simplify things a bit. So 32 negative 32, we can just pull out the 32 in there. So we get 32 times 1 negative 1. And the magnitude of that is going to be the absolute value of the constant times the magnitude of 1 negative 1, which of course that is just root 2. So 32 root 2 is a little simpler way to see what's going on here. This is a useful thing to remember. If you can pull out sort of a common factor and then take the magnitude, it sort of simplifies things a little bit. And so when we divide by 32 root 2, we just get 1 over root 2, negative 1 over root 2. Of course, if you did 1 over root 2048, you'd still be correct. That'd be a correct answer. But this is sort of a simplified answer there. So that's a unit vector pointing in the direction of max increase. In other words, a unit vector pointing in the direction of the gradient. And the max rate of increase is just the magnitude of the gradient, which we just said is 32 root 2. We good?
Wait, so how did we get the maximum there? Because we go from like the unit vector 1 over root 2 to negative 1 over root 2, and then did we just multiply that by the 32?
So we know the max rate of increase is just the magnitude of the gradient, and we already calculated the magnitude of the gradient here when we were calculating looking at the unit vector in the direction, because we need to divide by the magnitude. We already calculated the magnitude. Does that make sense? So the theorem says the max rate of increase is the magnitude of the gradient. Does that clear things up?
Yeah.
Okay. All right. And then let's look at a tangent plane to a level surface. And let me just write this down as a theorem. So suppose the point P. So P is a point ABC. Is going to be a point on the level surface f of x, y, z equals k. So remember a level curve for a function of two variables, we have level curves, right? You have f of x, y equals a constant. For functions of three variables, we have level surfaces, right? The set of all points where our function is the same value is going to give us a surface in R3. So we have a point on a level surface of a function. So if the gradient of our function at the point is not 0, then the gradient of f at the point P is going to be normal to the tangent plane. Whoops. For the level surface at P. So we have a level surface. We'll look at some examples of this. So we have a level surface of a function. Then the gradient of that function at some point on the level surface is going to be normal to the tangent plane to that level surface at that point. Moreover, you can directly use that to get the equation of the tangent plane to the surface. So the equation of the tangent plane in question is the partial of f with respect to x. So we know that the normal is the gradient, which is the partial of f, partial of y partial def with respect to x, partial def with respect to y, partial def with respect to z. So that's our normal vector. So those are going to be the coefficients here. So that partial def with respect to x times x minus a plus partial def with respect to y at our point y minus b. Make sure that's legible. And then partial def with respect to z times z minus c equals 0. And so don't be confused. I'll explain this in just a sec, by the fact that here we just talked about finding the equation to a tangent plane to a surface before. And yet here we're learning another equation to a tangent plane of a surface. Well, the thing is, these are two different surfaces. One is the graph of a function of 2 variables, and one is a level surface for a function of 3 variables. But it turns out, I'll show you in a sec, this equation actually gives us exactly the other equation in the case of a graph of a function. And we'll show that in a sec. But let's do an example of this. So suppose we have the surface so find the equation of the tangent plane to the surface 4x squared plus 9y squared plus 16 equals z squared at the point 2, 1, 3. Okay, so first thing we need to do, hang on, I think I wrote that. No, I think that's minus 16. It doesn't actually matter here, but yes, okay, yes. All right. So first thing we need to do is, so in order to use this formula, we need to write this surface as the level surface of some function of 3 variables. So we need to get everything on one side, essentially. So you can get everything but constants on one side. It won't actually make a difference. But let's just move everything over to one side and set it equal to 0. So we need to write as some function of x, y, and z equals a constant. Doesn't matter what that constant is. You could just move everything over to one side, set it equal to 0. It doesn't matter. So we have 4x squared plus 9y squared minus c squared minus 16 equals 0. If you like, you can throw the 16 on the other side. It doesn't matter. But this guy here is going to be our function of 3 variables. And this is going to be the level surface, f of x, y equals 0. Does everyone understand this point? You just need to throw all the variables on one side. And the thing involving all the variables, that's your function. Okay, so our normal is going to be the gradient of f at the point 213. So we need two things for the equation of a plane. We need a point and we need a normal vector. We know our point 213. We know our normal vector is the gradient of f. Oh, sorry, the gradient of big F. We use big F just sort of for a reason. I'll explain in a sec. At the point. So let's find the gradient of f. So without plugging in our point, what's the partial of f with respect to x?
Is it 8x?
Right, it's 8x. And then the partial of f with respect to y, it's going to be 18y. So that's the partial of f with respect to y. And the partial of f with respect to z is going to be negative 2z. That's a gradient of big F. So then our normal vector is going to be the gradient of big F at the point 213. So plugging in x equals 2, y equals 1, z equals 3. We get 8 times 2, which is 16. 18 times 1, which is 18. And then 3 times negative 2, which is negative 6. And so that's our normal vector. And so then plugging this into our equation of a function, we have a point. We have a normal vector. So our equation is 16 x minus 2 plus 18y minus 1 minus 6 z minus 3 equals 0. So the point is, we take the equation of our surface, we throw everything on one side, just throw everything on one side, set it equal to 0. So everything on the left-hand side is going to be your function. And this is going to be the level surface, that function equal to 0. And so the normal at your point is just going to be the gradient of that function at the point. And then you have a point, you have a normal, throw it in your formula. Okay, any questions about this? Okay, so to avoid some confusion, let me explain how the equation we already learned, you can actually get from this equation here. They're actually essentially the same thing. So we learned before so the equation for the tangent plane to the graph of a function of two variables at the point AB, f of AB, we learned that is just z is equal to f of AB plus the partial of f with respect to x at AB, x minus a, plus the partial of f with respect to y at AB times y minus b. So that formula only works if your surface is the graph of a function of two variables. This one is actually more general that we just learned. So for instance, the thing we just did, we cannot write this as the graph of a function of two variables, because in order to do that, we would need to write it as z equals a function of x and y. So we need to be able to get z by itself. If we wanted to do that, we'd have to do z is equal to plus or minus the square root of the stuff on the left-hand side. So we can't write it as the graph of a single function. But what we can do is we can show how these two are actually the same thing. How you can actually, if you know this equation here, you can derive the second equation. So the graph of a function of two variables so the graph of f of xy is just the surface z equals f of xy. Right? So what we can do is we can do what we just did in the previous case, throw everything on one side and write it as little f of xy minus z equals 0. So we're going to take everything on the left-hand side there to be now a function of three variables, x, y, and z. So now this is a level surface, big F of x, y, z equals 0, where big F of x, y, z is just our function of two variables minus z. So our gradient of f is, so the partial big F with respect to x, so it's just the partial of little f with respect to x minus 0, because z is treated as a constant. The partial of big F with respect to y is the partial of little f with respect to y minus 0, because z is a constant. And what's the partial of big F with respect to z going to be? Not so big F is our function of x and y minus z. It's going to be -1, right? Because when you take the partial of little f of x, y, that's just a constant, right? Because we're treating everything but z as a constant, so that's going to be 0. And then minus z becomes -1. So that's going to be the normal to our surface when we write it in this form. And so our function is just going to be partial of f with respect to x at AB, x minus a, plus partial of f with respect to y at AB times y minus b, plus -1, so minus z minus f of AB, whoops, set it equal to 0. And we could just rearrange this to get exactly, hang on, exactly this formula we learned before. Right, all we're doing is we're throwing z on the other side. Okay, but the important bit is, so if you are going to remember both of these guys, remember this equation here. This only works for surfaces which are graphs of functions of two variables. So if you get z by itself, z equals f of xy, you can use this formula. For the other one, or sorry, for this equation here, that works for anything, but you need to write it as the level surface of a function of three variables, right? So you need to get everything on one side. And then that everything on one side is going to be the function of three variables. Sorry, I understand that's maybe a little confusing, but does anyone need any more clarification on that? Because it's important that you don't get those mixed up. If you only have room in your brain for one, which I totally understand, I would remember this. I would remember this formula. And if you see, like, say you have the graph of a function of two variables, that's the surface z equals f of xy. We'll just get everything on one side, write it as f of xy minus z equals 0, and then use this function, or use this formula. Does that make sense? I'm going to take your silence as a yes. All right, so that's it for this chapter. I'm going to head over to the office hour Zoom. So I will see you there. And if not, I will see you all tomorrow. Have a great rest of your day. Bye, guys.
Thank you.
Thank you.
Mm.